So the next problem in our problem number 17 is system of matrix and the Cramer rule. We are asked here to transfer both equations that were given in the initial part of the problem to a matrix equation and calculate by using the Cramer rule how an expansionary monetary policy will affect an equilibrium level of our income. So here we can see that there are two equations given initially in the problem set, where the first one represents our IS curve and the second one represents our LM curve. As we have done in the introductory session regarding the Cramer rule, what we do is to actually gather our endogenous variables to the left hand side of the equation, which would give us for the IS curve 1 minus C1 minus B1 multiplied by Y plus B2 multiplied by I, and for the right hand side equation we would have CO minus C1T plus BO plus G. For the LM curve, when we transform the two endogenous variables of Y and I to the left hand side equation, we would have d1y minus d2i is equal to m over p minus do. So we have these two systems of linear equations, and what we have to do now is to transform this into a matrix representation. So the first thing we have to do is transformation, which can be written as, first we would represent our A matrix as we have seen earlier. So I would have 1 minus C1 minus B1 as a coefficient of Y in our IS curve, and B2 as a coefficient of I in our IS curve. Similarly, we would have D1 as a coefficient of Y in our LM curve, and minus D2 as a coefficient of I in our LM curve. We still have Y and I in this case, and this would give us the matrix of CO minus C1T plus B0 plus G, which is again followed by the IS curve, the LM curve. The next thing that we have to do is we have to take total differential. So when we take the total differential of our matrix equation, which is given above, we would have a value which look like this. Multiplied by dy and di. The total differential of our IS curve is pretty much straightforward. dc0 minus c1 multiplied by dt plus db0 plus g. However, the total differential of our LM curve is represented by the formula dm multiplied by 1 over p minus m over p squared dp minus d d0. So this LM curve, or the total differential of our LM curve, is looking a bit different or bit complicated than what we have seen so far. This is actually concerning the product rule in a total differential. So I would just try to derive how we come up with a value of this for the total differential of our LM curve. So when I'm saying the total differential of d1y minus d2i, m over p minus d0, what we are really saying is that the partial derivative of m over p minus d0 with respect to m, our first variable, multiplied by dm, plus the partial derivative of m over p minus do with respect to p, multiplied by p, and the last term would be partial derivative of m over p minus do with respect to do multiplied by do. So if we take the derivative of m over p minus do with respect to m, we would get 1 over p as a value, and we still have dm here. This second term is if we take the derivative of m over p with respect to p, this is again the product rule, so we are actually taking the derivative of m p raised to minus 1 minus do with respect to p. So this is done by usually by taking this minus 1 to the front, so it will give us minus 1 m p minus 1 we would have still here, and we would subtract 1 here, and this minus do is not going to be any more a problem. So this would give us minus m p raised to minus 2, which can be rewritten as minus m over p squared. So this term is entirely multiplied by dp, as we have seen earlier. So the partial derivative of this term here can be written as, I have mentioned it earlier, m over p squared multiplied by dp. So the last term would give us minus 1 multiplied by d0, so I would just write d0 here. So this is basically how we come up with the total differential of our IS and LM curve, which is given by the total differential formula that you have seen on previous occasion. So after the total differential, what we have to do is, like we always do, we have to have our assumptions clear. So our assumptions is like dCO is equal to dt is equal to dBO is equal to dG is equal to dDO is equal to dP. So all of these terms should be set to 0. If I set all these terms to 0, I would have a simplified total differential, which would look like so the entire term of our IS curve would be changed to 0 because all of the d's here are actually 0. So we would put 0 instead of the entire term. For our LM component, what would be left is 1 over p multiplied by dm, since we have said dp and d0 are equal to 0. Now the next step that we are going to do is to identify our determinant and to solve for dy and di. So for dy, our determinant would look like, first I would have the values of di or the coefficients of dy in this case, which is 1 minus C1 minus B2 for IS curve and D1 for the LM curve, and I would replace it with our B matrix here. So I would have 0, 1 over P dm as a representative of our dy coefficients here, and the second term remains the same. This again should be divided by the determinant of our A matrix, which is 1 minus C1 B2 multiplied by B2 D1 minus D2, and this is again a determinant. We have already seen how to solve the determinant, so I would multiply 0 with minus D2 first. I would take the diagonal here. I would put a minus sign here, and I would also take another diagonal, which would give me B2 multiplied by 1 over P dm. This entire term is divided by the determinant of this matrix. So first I would take 1 minus C1 minus B2 multiplied by minus D2 minus the other diagonal term, which is B2 multiplied by D1. So simplified, we would have dy is equal to minus B2 multiplied by 1 over P dm divided by 1 minus C1 minus B2 multiplied by minus D2 minus D1 B2. So the question indicates that we wanted to know how an expansionary monetary policy would affect the equilibrium income. So we want to know if my monetary policy is expansionary, by how much would be the impact of this expansionary monetary policy on my income. So mathematically, this is again to say we want to know what would be our dy divided by dm, that is to say the change in our income with respect to the change in our monetary policy or the money supply M. So this is again mathematically to say what would be our dy over dm. So if I take dm to the left hand side of this equation, I would have dy multiplied by dm is equal to, I would have a minus here, 1 over P multiplied by B2 divided by, if I take a minus term for the entire denominator here, I would have D2 multiplied by 1 minus C1 minus B2 plus D1 B2. So here on the numerator and denominator we have two minuses. We can just cancel out these two minuses, and our equation can be simplified and written as our multiplier would be 1 over P multiplied by B2 divided by 1 minus C1 minus B1 multiplied by D2 plus D1 B2. So this term is a positive term, as you can see, and this positive term should be represented by greater than 0 notation at the end of our equation. So the next item is 17.3 again, matrix system and Cramer's rule. What value would the multiplier take if B2 converges to 0? So again, we would take the limit of B2 converging to 0. We have already identified that our dy over dm is given by the formula 1 over p multiplied by B2 divided by d2 multiplied by 1 minus c1 minus b1 plus d1 b2. So in this case, if our b2 is converging to 0, the entire term would also converge to 0. And therefore, the denominator would also converge to 0 because our b2 is actually appearing on the denominator here. Then this is again to say the entire term will converge to 0. I can also show you how we can transfer this equation to more of a simple equation to see what the impact of the convergence would look like. So we have said that we want to determine the limit of our equation when b2 converges to 0. We had 1 over p b2 divided by 1 minus c1 minus b1 multiplied by d2 plus d1 over b2. So this formula is nothing but saying b2 over p on the numerator, and the denominator remains the same, 1 minus c1 minus b1 multiplied by d2 plus d1 d2. So if I can multiply both the denominator and the numerator by 1 over b2 and 1 over b2, my b2 would cancel out from the numerator, and I would have a formula which looks like 1 over p is divided by 1 minus c1 minus b1 multiplied by d2 plus d1 multiplied by d2 divided by b2. This can be again simplified by saying 1 over p divided by 1 minus c1 minus b1 multiplied by d2 divided by b2 plus, since we have, this should be b2, sorry. Since we have b2 here, b2 would cancel out with the denominator, so we would be left with d1 here. So if b2 is converging to 0 in our case, what we are saying is this entire term is converging to 0, and therefore the denominator converges to infinity. So this denominator is having this term here, and this term is converging to infinity because our b2 is converging to 0. So this is again to say if 1 minus c1 minus b1 multiplied by d2 divided by b2 is converging to infinity, this is caused by the fact that our b2 is converging to 0. If b2 is converging to 0, this is to say b2 is becoming really small number. So this makes our entire term of 1 minus c1 minus b1 multiplied by d2 divided by b2 to converge to infinity. So infinity plus d1 would be our denominator as the entire sum of what we have just derived. So if this entire term is converging to infinity, that is to say our entire formula 1 over p divided by a term which is converging to infinity would give us a value of 0, because a number divided by a very, very, very large number which is actually diverging to infinity would give us a value of 0. So this is why we are saying if B2 converges to 0, then the term D2 multiplied by 1 minus C1 minus B1 divided by B2 is also converged to infinity. Then the whole term converges to 0, because the whole term which is converging to infinity appears on the denominator.